Hello, today we're gonna talking about lecture 2. Lecture 2 is still about chapter 1. 2 points here. The first, kind of like extended analysis of how to describe two variables. They're either two numerical variables or two categorical variables. Point 2 is to touch a little bit about the data connection. As I explained in the first lecture, the starting point of this course, of course, is assume that the data sets are already ready. But I really like just touch a little bit about this data connection. In my opinion, it will make us understand deeper about the data and somehow could make our data analysis better, I think. So we have 3 parts for today's video. The first part is how to describe 2 numerical variables. Second part is about 2 categorical variables, and then the third part is the data connection. For the 2 numerical variables, we already talked a lot in lecture 1. Basically, we're talking about how to describe it. We have 2 ways, right? Either the graphical way or numerical way. So for the graphical way, basically the graphical tool, that is what we mean by scatter plot. Scatter plot. So the key question is here, because we have 2 variables, right? We want to know the relationship between the 2 variables. That's equivalent to say, when one variable increases, what does the other variable do? So for the other variable, it has 3 choices, either to increase, to decrease, or not do much of anything. As we know, scatter plot is a graph just to describe 2 potentially related variables. Here we just put x and y. How to construct scatter plot? Each point is a pairing, right? So we put x in the front and y in the second as indexes for a point, and then connect the points together. That's what we mean by scatter plot. That shows y against x. But this is a scatter plot, shows income against education. The x variable here is the education, means years of school. Income is the y. This is y. So each dot is a variable with x. For example, here is 8 years of school, and here is 8. Yes, here 90. So each dot is a pair of x and y. After we get a scatter plot, we could eyeball a line, straight line. What does this scatter plot tell us? Because after we eyeball a line, then we could just say the relationship of the x, education, income, and y is what? Is positive. That means whenever we increase the x, more years of education, we would observe also the increase of y. That means more income. So basically it says higher education, higher income. That's the relationship between. So this is a very encouraging news for us, right? Because we're here to get degrees, and then the degrees will help us to earn more income in the future. That's basically the idea. Other than the graphical tool as the scatter plot, we could just think of like numerical tools to describe. Here, covariance. We're talking about the covariance in lecture 1 also, and this is the formula right here. Because for most of us, this might be your first time to use this kind of formula here, right? Actually, this formula is kind of complicated, okay? That's why I would use an example to show us how to use this formula. As we know, this covariance actually is a very good indicator of the relationship, right? A positive value indicates positive linear relationship. Negative value, negative linear relationship. If it's 0, that means x and y have no linear relationship. Here we got to be a little bit careful, because you see we always put this linear here. Linear, right? So the covariance actually is the measurement of a linear relationship. Especially when we say whenever the covariance is 0, we could not say there is no relationship between x and y. We need to say there is no linear relationship, okay? But there is a drawback for the covariance. Like the variance, yes, the covariance, is difficult to interpret because it's sensitive to units of measurement. What does it mean? Let's take a look at the example here. So yes, this is exactly the example we're talking about. The x is the education and the y is the income. We have 8 pairs, right here. And we're going to use these 8 pairs of number to calculate this covariance between x and y. All right. To make things easier, we come up with a table. Okay, right here. You see, this is the formula right here. We have to practice 2 points here. Number 1, we need to know what does this I mean. I is index, right? Because we have 8x and y. So each of them we index as 1, 2, up to 8. So here I goes from 1 to 8. Here n equals 8. The second point we need to practice is what? Is this sum. This is a Greek letter. We can call it as a sigma, but here I put as a sum, as basically just this note, okay? What does this mean? For the sample mean, for both x and y, this one is kind of easy, right? Because we did practice this in lecture 1. Remember the formula for the sample mean is what? For x bar is 1 over n sum xi. Here is same thing, right? I goes from 1 to n. Yeah, this is the first practice. And the y bar is the same thing. To get x bar and y bar, actually for x, we just add all of them together, right? And the sum is going to be what? 32, okay? If we want to add y together, that is going to be much harder, okay? Why? If you're a calculator, you can do it, right? You add all these 8 numbers together, end up with 462. And then we got this part, right, for x. And n equals 8, then x bar is going to be 32 divided by 8, which is 4, okay? And for y, here, the same idea, the sum divided by 8. So in this case, it's going to be 462 divided by 8, which end up as 57.75, okay? Because use the calculator. We should have no problem about this, I assume, get the sample mean. Here, actually, we already practiced this sigma, right? The sum. So basically, add all of them together, and then the same thing for y, and then divide by 8. That's how we get this. What is this column? Is xi minus x bar. We have x bar equals 4, right? Xi, the first one, x1 is 3. 3 minus 4, which is -1. And the 4 minus 4 is 0. 6 minus 4 is 2. And 2 minus 4 is -2. 5 minus 4 is 1. And 0, 4, and then -4. We just subtract this 4 x bar from each of those 8 xi's. As I talking about in lecture 1, if we sum all these xi minus x bar together, what do we get? Think about this one. See, -1 plus 2. This one is cancelled out, right? 2, -2. 1, -1. 4, -4. So this end up with 0. For y case, is a little complicated. This we may need a little bit more calculation. Actually, it's not that hard, right? You can just do it right here. I would strongly recommend just try this table yourself with the help of the calculator. Because of time, I'm not gonna go through each of those. And not surprisingly, this sum should be 0 also. Okay, I do one at least. Y bar is 57.75, and then 45 minus that is gonna be -12.75, right? And for 56, it's gonna be -1.75. For 85, is gonna be 27.25. Okay. For this one, please just finish yourself after class. Here, I really want to save some time. After we got xi minus x bar, yi minus y bar, then we got this product term. Product term means what? Means use this number, -1 times -12.75. What do we got? Is 12.75, right? And then we have 0 times -1.75. 0 times that is always what? 0. And then we use 2 times 27.25, which ends up with 54.5. We can do the rest. We get each of those numbers, and then we would get a sum here. This sum definitely is not 0, okay? In this case, yes. Please finish this one yourself after that. After we get this one, actually this is exactly the sum of all those products, right? So this basically equals the sum of xi minus x bar, yi minus y bar. In our case, I goes from 1 to 8, right? Equals that. After we get that, basically we get this part of the formula. Is that correct? Right? Then what is this covariance? We got this sum part is 358. And then don't forget that the front term is 1 over n minus 1, which is 1 over 8 minus 1, and then 358. Okay, that's what we got for sample covariance. This is about 51.143. Okay, that's how we got this sample covariance between education and income. Please practice after class, okay, with the help of the calculator. Make sure you understand how to use this formula. This is the kind of like the key to complete the table, okay? So we just now we have this xy equals 1 over 8 minus 1 times this guy, 358. Because just now we had a claim which says the sample covariance is very sensitive to the measurement unit. Remember, for this income actually is $1,000. That's the unit. So 45K, right? That's usually we say it in the real life, like the salary. Okay. Now think about we put a 45 here, right? But we just because we already know this unit is $1,000. But what if we change the $1,000 into $1? Then we put 3 zeros in the end, right? Right, each of them. And then the sum is going to be also 3 zeros. Think about this one. Now this y bar is also 3,000 times, right? And then this whole thing is 3,000 times. This something is 3,000 times. Then end up with, excuse me, 1,000 times. Ends up with this sum gonna be 358,000. We do the same thing here, right? Now it becomes 1 over 8 minus 1, 358,000. Now you can see if with the unit of $1 instead of $1,000, then the covariance will become 1,000 times the previous one. I repeat this again. Originally, we used this $1,000 as the measurement for the income, okay, for Y. So we'll end up with the covariance between the education and the income as this guy. But after we use $1 as the measurement unit, then we end up with this covariance between the education and the income. You know, basically the same thing, right? These two variables do not change, education and the income. But in one case, the income is measured $1,000. The other case is measured in $1. Ends up with two different covariance. The second one is 1,000 times of the first one. This kind of like what? Like a little strange in the real life, right? So that's basically says what? Says right here. This covariance actually, whether is positive or negative, only give us a direction. What do I mean by direction? Either positive or negative. If the covariance is positive, that means the relationship is positive. If it's negative, the relationship is negative. Okay? So, but how big the strength of the relationship? We cannot get the strength out of the covariance. Why? Because here, if this covariance can measure the strength of the relationship, then how could, if we change the unit, the value has changed also? That's the drawback for the covariance. That's why we need to go a step further to introduce this notion, correlation coefficient. You can see correlation coefficient, we still put the covariance on the top, but on the bottom, we have this standard deviation of x and y, okay, right? So we kind of like an idea of what? Like we want to scale this covariance by the product of the standard deviation of x and y. Back to the educational income example. So this is the sample covariance we got, and then we need to divide it by the standard deviation of x and y. Of course, this is extra work, right? Variance of x, this is the formula, okay? 1 over m sum xi minus x bar squared, right? I goes from 1 to n. The same thing for y, okay? You just replace x with y. You can see here we have the, what does this mean? We have xi minus x bar right here, right? And then you square it. Negative 1 squared as 1, 0 squared as 0, 2 squared as 4, negative 2 squared as 4, right? 1, 1, 0, 4, 16, negative 4, 16 also. And then we add all of them together, right? Now, in this case, it's going to be 1 over 8 minus 1, 42. So, yeah, this is a perfect number, okay? So it's 6. That's how we get this variance as 6. And then we take a square root of 6. That's the standard deviation, right? So the same thing for y. That's how we got this sx and sy. And then we end up with a number which is, in terms of the scale, is much smaller, right? Because the sample covariance is over 50, but here is only less than 1. How are we going to interpret this number? You know, it turns out this sample correlation coefficient is really good in terms of unit free. Because as we talking about just now, the sample covariance is not unit free, right? It is sensitive to units. But here, finally, correlation coefficient is unit free. What does that mean? So back to our education and income example. So for this education, either measured in $1 or $1,000, we do not care because it ends up the same thing as 0.91. Why? Because if it's measured in $1, then this one is augmented by 1,000 times, right? But this standard deviation is x, the same thing, but for y, it becomes 23 times 1,000. You can see we have multiplied by 1,000 on top, and then the bottom, this one get cancelled, right? So that means if the income is measured in $1, then this correlation coefficient is still 0.91, does not change. That's what we mean by unit free. Also, the nice part of this correlation coefficient is what? It falls between -1 and 1. Basically, the absolute value is less than at most 1. So if it equals 1, that's a perfect positive relationship. If it's negative, that's a perfect negative relationship. Whether this one is positive or negative, it measures the so-called direction of the relationship. Okay, so this is the same as the sample variance, right? Because sample variance can also be an indicator of the direction, right? Either positive or negative, depends on whether it's a positive value or negative value. But other than that, correlation coefficient also give us the strength. Whenever it's close to 0, that means weak because it has 0 in the middle and then -1 and 1, right? So if the correlation coefficient value is around this 0 part, okay, that's kind of weak. So yeah, for example, like a 0.12, right? This is a weak positive relationship. If it's negative 0.12, that's a weak negative relationship. But whenever the value is close to 1, that's a strong positive relationship. Whenever the value is closer to -1, that's a strong negative relationship. So here we could have a very clear cut about whether the relationship is strong or not. Okay, this is the property which the sample covariance does not have. And from this chart, we want to show at least we have a rough idea about how strong, how weak, right? About either positive or negative relationship for the R, because we know those are what? Scatter plot, right? And scatter plot is a graphical tool to describe the relationship between two numerical variables. Also, now we have the correlation coefficient is a numerical tool. We could, based on the scatter plot, correspond to the values. All right. For example, if the scatter plot is in a perfect line right here, you can see. Of course, this line is positive sloped. It's upward sloped, right? That's a positive 1. And if it's negative sloped, it's -1. For a strong positive relationship, you can see those dots, they are not exactly perfectly as this R equals 1 case, but they are still what? You can easily eyeball a line, right? The same thing for the negative part, you see. Because those dots are scattered around very closely to this line. Think about for the weak positive case, the first one, you can see those dots are pretty much spread it out, right? Here and there. Yes, we could eyeball a line, but this line is gonna be like this because we could have so many points which are so far away from the line. The same thing for this one. Here is gonna it's negative relationship right here. You can see compare with 0.33, 69 is larger, and you can see you can eyeball a line which will have more dots are closer to this line. And the same thing for what? For the R equals -0.64, we can eyeball a line. Compare with the -0.08, those dots are kind of closer, right? So here, first we need to know, whenever you see a scatter plot, you should know in your mind a rough idea about what that R value gonna be. Basically just 2 points, right? Point number 1 is the direction of the relationship. So that's exactly depends on the slope of this eyeballed line. If, for example, in the first row, those 4 lines, they are upward sloped. So all the R's are positive. For the second row, all the lines are what? Downward sloped. That means slopes are negative. That's corresponding to R also negative. Okay, this is about the direction. Second point is about the strength. After you get the line, and then you just check the line and the points, the dots. If the dots are very close to the line, that means approximability is really good. That means the value either is very close to what? 1 or negative 1. Otherwise, like the first two, right? These two, here and here, they are pretty much scattered around. Then that means the strength of the relationship is kind of low. So you can see it is very close to 0 on the right side, is very close to 0 on the left side. Yes, that's what I mean by from left to right, the strength of the linear association between x, y increases. Okay. The last point I want to say is about correlation coefficient, because sometimes we could have a correlation coefficient equals 0. For example, like the first table, why this is 0, we can do a little calculation here. See, in this case, for the x, sum is 0. That means x bar is what? Is 0. And then the sum y is 2, then y bar is what? 2/3, right? Because in this case, n equals 3. And then since x bar is 0, xi minus x bar basically is -1, the same thing, right? And then end up with 0. And then for y, I minus y bar case is 1 minus 2/3 is 1/3. 0 minus 2/3 is -2/3. 1 minus 2/3 is 1 over 1/3. And then you add up with 0. Okay. Now think about the the product term. Okay, so -1 times 1/3, which is -1/3. 0 times -2/3 is 0. And 1 times 1/3 is 1/3. And then you add together as what? 0. So since this sum is 0, what is the SXY covariance between x and y here? Is 1 minus 1 divided 3 minus 1, right? And minus 1, then 0, ends up with 0. If the covariance is 0, right? And the R, remember R equals the covariance divided by standard deviation of x and y. So whenever the top term is 0, then they end up with 0, okay? The same thing for the second table, okay? N equals 3 also. And then for the second one, you can see x equals 0, 1, 2, and then the sum is 3. Y equals what? Because the sum is 3. And then x bar is the same as y bar as 1, okay? Whenever this is 1, then we just do the same thing here. -1, 0, 1. So this is 0. I minus y bar, because y, 3 y's are the same as 1. The sum is mean of y is 1. So 1 minus 1, 0, 0, 0, 0, right? And then since y minus y bar always 0, then you multiply with the xi minus x bar, still ends up with 0, 0, 0, okay? So here, obviously, sample covariance between x and y and is 0. But here we're going to be a little bit careful, because think about this case, because the R, other than the sample covariance, we have to consider the standard deviation of x and y. So in this case, for the y case, think about it, because y does not vary at all, it's 1 all the time. So in this case, here is 0, 0, 0, right? You see right here? So the variance of y is 0. Now we have a problem, because in this case, this R actually is what? Is 0 divided by 0. Because we know this denominator can never be 0. If we have a 0, then we would say This is not defined, right? So in the second case, actually, we could not find a R for this second table. The first one is 0 because we know both this one and this one is not 0. Okay, please figure it out after your class why this is not 0. I'm pretty sure you can do it right here. Okay, so and if we plot these two tables, you can see for the first one, x is 0, y is 0, x is -1, y is 1, x is 1, y is 1, right? So we have 3 dots like this. You can see these 3 dots actually, remember the correlation coefficient is to measure the linear relationship. In our case, this linear relationship, because those are kind of, they are not in the same line, right? So in order to get a eyeball line, which gonna be what? It's really hard. Okay, so actually the relationship between y and x is like what? Y equals x squared, right? You can see, or y equals absolute value of x, which is like this. Okay. What does this mean? So the relationship between y and x actually is not linear, right? But a non-linear relationship. That's why this r equals 0. Okay, r equals 0, that means what? Means no linear relationship. And for the second table, if we plot 3 pairs and xy, we get 3 dots. You can see no matter what value of x, either x is 0, 1, or 2, y is always 1. You see, it's flat. So in this case, y does not change when x changes. In this case, how to interpret, because in this case r does not exist even, right? Because we have a 0 denominator. Because how are we gonna interpret this one? You can see right here, seems like in this case r does not really work here, okay? Because r does not even have a number, okay? But we can see here y is what? Is kind of totally ignoring x, right? No matter x is low or high, y is always 1, is flat. Those are two interesting examples about the correlation coefficient. About the practice of the correlation coefficient in real life, we gotta be careful about correlation does not imply causation. What do we mean by causation? Causation means, like the first example we're talking about, education and the income. We could say education caused the income. What does that mean? That means higher education means a higher income. So in that case, what is the cause of the higher income? Is the higher education. But in some case, we cannot. For example, like here, if we just calculate the correlation coefficient between the age and the income, and then, of course, this number gotta be what? Positive. The fact is, if we observe the real life, we will find that, right? People who are older tend to earn more money. But can we say age is the cause of the income? Not necessarily, right? And also we have the temperature and the latitude. As latitude increases, temperature tends to decrease. Can we say latitude is the cause of the temperature? Here, we want to emphasize correlation is only a statement of numerical facts. It says nothing about cause and effect. As we'll see, causation is a much more complex matter. Those similar questions here, okay, please read it yourself. Exam 2, the same thing. And the exam 3, I really want to say something. This is a very cool picture, okay? So the X in this case is the chocolate consumption, okay? This is X. And the Y is what? Nobel laureates per 10 million population, okay? This is Y. And then we plot each of those many countries. And then this kind of like a dots, right? Like a dots. And then if we eyeball a line right here. So this line is pretty much like what? Like this, right? So you can see this R is pretty big. It's almost not 8. R is almost 0.8. So the positive relationship is strong. But how to interpret this strong relationship? Can you say chocolate consumption is the cause to win Nobel Prize? That's not true, right? Does that make sense? So I hope this part will explain what correlation coefficient can do and what correlation coefficient cannot do, okay? It's just the numerical facts. It's measure the linear relationship, just the correlation. Is not the cause. All right. I think this is the end of the part for 2 numerical variables. Now we're talking about 2 categorical variables. For 2 categorical variables, as in the lecture 1, we're talking about the contingency table, right? Contingency table, we just list these 2 variables. One is about, in this case, it's about the race, okay? And then the other one is the genotype. Okay, we're talking about this one in lecture 1. And then we count how many falls into intersection of the African American and CC type. That's 16. And then each number is the intersection of the column and the row, right? That's exactly the overlap of that 2 subcategories. We put a sum. This is the column sum and row sum, and then here is the total. So this total is we observed 595 persons, okay? We have this marginal totals right here. That's the contingency table. Contingency table sometimes can be called as a 2-way table because we have row and column, right? 2 ways. Like the relative frequencies table for this distribution 1 categorical variable, contingency table can also be converted to show proportions, right? Because just now they are just counts. Now we could do the proportions right here. For example, this is the proportions. This is called the row proportions. What does that mean? Row proportions, basically we use the row sum to divide the counts for each row. Okay, 16 divided by 27, 6 divided by 27, 5 divided by 27, and the 27 divided by 27. And then the same thing divided by the second row divided by 55, the third row divided by 467, okay? That's how we end up with the sum. The row sums, right, are always 1 because you just divide exactly for each row by that row sum. And then we can also do the total column sum. We divide each column by the column total. Out of this 2x2 table, contingency table, we come up with a notion is called relative risk. And then this definitely is the key because we're going to use this a lot in the biostatistics. So we come up with a table. I hope this could serve kind of like a model. Okay, so we have 2 variables. This is one variable is about outcome. This is the variable. And the other variable is about groups. Okay, for the outcome variable, it has 2 categories, outcome A and outcome B. And then for groups variables, we have 2 groups also, is 1 and 2. We observed A, B, C, D as the corresponding counts or frequencies. And then we have the row sum, right? And the column sum and the total. Here we usually will put as grand total, okay? Or grand sum. Based on this table, we could define a relative risk of outcome A in the hypothetical 2x2 table, right? That's figure 8 right here. First, we're talking about the risk. For the group A, what is the risk of the outcome A? That means for group A, the total is A plus B, right? And then we observed little a of outcome A. That's the risk of outcome A, the proportion of outcome A in group 1. And then for group 2, the same thing, right? To get outcome A is C over C plus D. So why this is called risk? Because in the real practice, we put these two groups, but the outcome, most of the time we say is a disease, right? For example, outcome A means COVID-19 test positive, got a COVID-19. Outcome B means not. That's, yes, risk. Basically, it's just the proportion. And then we have two proportions, right? What do we mean by relative risk? Relative risk, we just take a ratio of these two, okay? This is for the proportion for A in group 1. And then this is A in group 2. Take a ratio of that. Exactly, we mean by relative risk of A compare group 1 to group 2, because 1 is on the top, 2 is on the bottom. And then if we switch, right, compare group 2 to group 1, then 2 is on the top and the 1 is on the bottom. Okay. Now let's take a look at the example. This is lip study. Okay. We have two groups, right? One group do not eat peanut. The other group eat peanuts. Now we do this called oral food challenge test. Just test whether they are allergic to individual failed this oral food test, correct? Because we are kind of related to the allergic to peanuts or not. This is like the outcome A, this outcome B. Here, the question of interest is whether the risk of developing peanut allergy differs between the peanut avoidance and the peanut consumption groups. The relative risk of failing the OFC equals the ratio of the proportion of individuals in the avoidance group who failed OFC to the proportion of individuals in the consumption group who failed OFC. So we have the risk for the avoidance group, right? Why is 36 over that? Because think about this one right here, right? Failed OFC in the avoidance group. That's 36 divided by 263. For the proportion of the failed OFC in the peanut consumption group, because that's 5 divided by 267. Is that right? Now we take a ratio. That's exactly what I'm doing here, right? That's what? That's the relative risk of the failing OFC for the group of avoidance to the group of consumption. After we get it, this is about 7.31. How to interpret this 7.31? So here we say the risk of failing the oral food challenge, OFC, for participants in the peanut avoidance is more than 7 times of those in the peanut consumption group. That's the way to interpret. So basically say to fail OFC, the avoidance group, the chance is like 7.31 times of the chance for the consumption group. We could have another example which is about the cardiovascular disease. That's one variable, right? And the other one is smoking, 2 variable. So we have 2 groups, smoker, non-smoker. And for the outcomes, we could have the CVD or no CVD. So this is the disease. Now we talk about the risk. Makes much more sense, right? We have A, B, C, D. Whenever we want to calculate this kind of a relative risk, I would strongly recommend a table like this, okay? Just make a table by yourself, like this. But the relative risk indicates what? The risk of CVD is equal for smokers and non-smokers, right? If this one, relative risk is 1. So in this case, so relative risk of the CVD with the smoker to non-smoker. That's A over A plus B and C over C plus D. That's relative risk, right? It's basically here out of A plus B, C out of C plus D. So if the relative risk is 1, means equal. The risk of CVD is equal for smokers and non-smokers. If it's risk less than 1, that means smokers are at lower risk than non-smokers, right? Right? And if it's greater than 1, indicates smokers are at higher risk of CVD than non-smokers. And if we put a very specific numbers here, take a look, right? We have 231 individuals. 111 are smokers, right? That's the row sum for smoker. 120 is gonna be what? Non-smoker. For 40 smokers and 32 non-smokers have this cardiovascular disease. That's basically 72 with the CVD. And then of course use 231 minus that is going to be this guy without CVD. And then we can figure out the rest of the numbers. Okay, so we kind of translate this wording into a table. Okay. With this table, we can the relative risk of the CVD compare smokers to non-smokers, which is exactly this one, right? You can see 40 out of 111 divided by 32 out of 120. Please make sure you got this table. That's the way to calculate the relative risk. But there's a caveat. A relative risk relies on the assumption that observed proportion of an event occurring in each group are representative of the risk or incidence of the event occurring within the population from which the groups are sampled. So what does this mean? So basically, here 231 people are randomly selected from a population, okay? And then after we selected 231, we observe whether they're smoker or not, whether they have CVD or not, okay? That's the way to design the study. The same thing for the LEAP data. But for this example, the same thing for the CVD example. In this case, take a look at how this study is designed. We're still interested in that, right? Association between smoking and cardiovascular disease, but the research uses a different study design than described in the example 1.22. For the new study, 90 individuals with the CVD and 110 individuals without CVD are recruited. 40 individuals with CVD are smokers, and 80 of the individuals without CVD are non-smokers. Should this relative risk to be summarized? This one is not, because you select those 200 individuals by two different criteria. First, you select what? With the CVD, and then select without CVD. It's like you choose them from two different populations. The correct way to do this, you should say, you just randomly select 200 people. Before you observe these 200 people, you do not know whether they have the CVD or not, okay? Whether they are smokers or not. That's the right way to do it. But here, you observed their CVD and you select it. Repeat it for 90 times. That's how you get 90 individuals with CVD. Whenever they're without a CVD, pick the one. This kind of design is a little weird, okay? And the same thing for this one. Yes, please read the details. I hope this one could help us to understand, to calculate, to interpret the relative risk better. Okay, I'm going to use the last several minutes to say something about the data connection principles, okay? It's always important, okay, to talk about this data connection, because that's really the first step. A clear, articulated research question is essential for selecting subjects to identify relative variables and determine how data should be connected. So first, we need to know what we want to do. After that, we're going to decide the population, and then based on the population, we decided to sample. That's the way, for example, like here, consider a bluefin tuna from the Atlantic Ocean have particular high level of mercury, such that they are unsafe for human consumption, right? This is the question. After we decided the population, how are we going to sample? So sample here, most of the time we use the so-called simple random sample. The simple random sample, that's the easiest and most often applied technique in the real life. Two designs to collect data. One is by experiment. Actually, in the biostatistics, we do a lot of experiments, actually. For example, like clinical trial for the new drugs, for the vaccines. This is a very important way to do it, experiments. And there is another way which is called observational studies. Observational studies basically are what? Surveys, okay? What's the difference between the experiments and the surveys? Experiments, basically you have to control the factors, right? You manipulate. It's like in physics, in biology, in chemistry, right? You do experiment. You create a lot of factors, a lot of conditions, most of the time in the lab. But for the survey, you do not interact. The only thing you do is kind of you observe, intervene any of the observation units. No, you do not. You just observe. That's the key difference. As I explained at the beginning, right, the focus of our course is how to analyze data instead of data connection. So here I just used these several slides to explain it. If you really want to know the details, please take a look, read the section 1.3 of the textbook, okay? And also I want to talk about a little bit of practice in real life, First, we gotta believe, right? Sampling from population, when done correctly, provides reliable information about the characteristic of a large population. Because of the time and the money, we could not just do observe each unit of the population, right? We only do part of it. That's exactly what we mean by sampling. Okay, and here in the U.S., several famous survey related to the health or the nutrition is this BRAF. Okay, this is a very popular one. The behavior risk factor for surveillance system. Okay, yes, I put a link here. You just hit the link. You can visit the website. This is for US CDC, and also for the World Health Organization, WHO. They conduct the so-called World Health Survey. Okay, you can also do it right there. Those are. I just want to show you. These are surveys, right? These are surveys. They are what? Observational study. Okay. We also have a lot of experiments, and such as the clinical trials. Pharmaceutical companies, pretty much for every drug, right? If they want to get approved by the FDA, they need to submit the report, right? This so-called clinical trial report. That's why they need a lot of statisticians, okay, for the pharmaceutical companies. What have we learned, okay? I kind of summarize what we did for this lecture, okay? So for lecture 2, we're talking about how to describe two variables, right? Describe two variables. If the two variables are numerical, we use the covariance correlation coefficient. If two categorical, we use a contingency table. Based on that, we have the relative risk. And then for the data connection, we need to know, after we know what we want to do, okay, set up the question correctly, and then we need to decide the population and the sample. How to get the sample? We can either use the experiment or survey. All right, I hope this video will help you to understand a little bit deeper and better about chapter 1. Okay, if you have any questions, let me know. Thanks for watching. Bye.